are going now to focus more into what we say as types of reactions. So now with type of reactions, we are looking at plus minus 25 marks in the final exam. So it being the 25 marks in an exam, it says to me I should be in a position of one, explaining now what we call acids and base reactions. Also, I should be in a position of working with what we call redox reactions. But now for today, the highlight now will be on working with acids and base. So as we build up to more complex situations, is then that we'll introduce later the redox reactions as part. So this allows us to be in a position of saying, when you get into your school, or when your teachers now arrive at this section, you will now be 2-3 steps ahead, and it will be a revision for some of you. So bear with us. It's a new lesson and a new experience for most of us in here, but I will always try now to accommodate any questions that are coming, and as well now put your resources close to you such that we can be now in a position of following each other correctly. So now with acids and base, we have what we call theories. So the theories basically governs everything that we want to understand about acids and base. So we had two scientists previously. One was called now Arrhenius. The other two were Lowry and Bronsted. So they were in a position of defining exactly what is an acid, also in a position of defining what is a base. So the two theories allows us now to build on them. The two theories allows us to have a proper foundation of exactly what is an acid, what is a base. I am aware in grade 8, grade 9, you always did acids and base, but more of the focus on what? On home-based acids. So in this case, we are expanding it a little bit further. We are taking it into now the real science context. So the real science context thereof is we are in a position of saying, let's allow us to use now the information now that is given to us. And I will kindly request again, people, please switch off your videos. They are disturbing everyone that is in here, as well as your mic there off. So now continue moving forward. I'm trying to find out now who is this one who doesn't want to switch off the mic. Kindly switch off your video as well as your mic. Switch off your video and your mic. And remember, next time, guys, when you log in, we don't want to see names like tab 8. The reason for that is we want to check your attendance thereof. So if you are tab 8, I can't exactly and necessarily tell who are you and how can I report your attendance thereof. So please, next time, just rename your tablet from tab 8 into something that, or your name, with a surname so that we can follow up exactly who you are. So going back to the lesson, as I was saying, so there's 2 or 3 scientists came up now with the theories of explaining exactly what is an acid as well as what is a base. So Arrhenius' model or theory says an acid is a substance that produces hydrogen ions or hydronium ions in water. And further goes on to say a base is a substance that produces hydroxide ions in water. So the difference now between the two is that if we have an acid that we are going to try and dissolve in water, that acid or that substance, if it produces now H3O plus, it is going now to be an acid thereof. So I will try to make a nice example of this situation. Let's consider a normal acid that we know, which is HCl. And we allow the HCl now to be dissolved in H2O. What will happen is we are going to have H3O plus Cl minus. But the reaction thereof says to me, I look now into this reaction. HCl donated a hydrogen to this H2O, such that we are in a position of having H3O plus. So what does this necessarily say to me? It says looking at Arrhenius saying is a substance that produces H3O plus. I can also incorporate the same thing and say, what is it that Laurie Bronsted is saying? Laurie Bronsted comes and say, an acid is a proton donor. So what is a proton? A proton is an H plus ion. Arrhenius says again, I'm repeating this now for the 4th time. An acid is a substance that produces hydrogen ions or hydronium ions. That means now H3O plus in water. So the example or the reaction that I wrote says now HCl as my acid, it dissolves or reacts now with this water to form now this hydronium ion and Cl minus thereof. So what does this say to me? It says now, when I look at an acid through Arrhenius, I need to see the formation of H3O plus. But when I look at an acid through Laurie Bronsted theory, then I must see an acid as a substance that will donate now what? A proton. And what proton is that? It's now my H plus. So it basically says they are saying the same thing, but one is focusing more on what? More on the product, which must be H3O plus. The other one is focusing more on the substance that will now do what? Will now donate a proton. If we fully understand, that, we can differentiate an acid in terms of the Arrhenius theory as well as the Laurie-Bronsted theory. So Arrhenius produces an acid, is a substance that produces H3O plus ions in water. Laurie-Bronsted, an acid, is a substance that now donates a proton. Manuku.
Good evening, sir.
Evening, Manuku.
Sir, I wanted to ask, would I be wrong if I was asked to differentiate between Arrhenius theory and Laurie-Bronsted theory? And I would say that Arrhenius theory explains an acid and a base if only they are in water, and Laurie-Bronsted explains acid and base in every case, like wherever.
Okay. That will be wrong, because remember, we must use the standard laws that are given. So we cannot necessarily say in water, in water, in water. The key thing is, according to Arrhenius, it must produce hydronium ion in water. So it's basically saying to me, define an acid according to Arrhenius theory. So when I say that, it basically says it forces you to emphasize the issue that it's a substance that will produce hydronium ions in water. If I say now define an acid according to Arrhenius theory, it must be now what? A substance that produces hydroxide ion in water. So you are right to say water according to Arrhenius, or an acid or a base according to Arrhenius, the emphasis should be it must be in water. So with Laurie-Bronsted, the focus now is the proton. What happens basically to a proton? So if the substance is donating a proton, that substance must be an acid. If the substance now is accepting a proton, keywords, then it basically says we are focusing more on Laurie-Bronsted.
So sir, what you're saying is
yes.
that they will always specify which theory to use, like which theory to use to explain acids and bases.
100%. Because if we just say to you, define an acid, we are not saying anything. The theories governs which definition or which law do we want you to use. So if I want you to tell me in terms of Laurie-Bronsted, I will say to you, define an acid according to the Laurie-Bronsted theory. Then you know exactly that we are looking for the movement of protons, a proton donor, a proton acceptor as the keywords that we will be now looking for.
Okay, sir, thank you.
Thank you very much, Manu. So I'm going now to explain the issue now of a base. So they say here, according to Arrhenius, is a substance that produces hydroxide ion in water. And then they say now a proton acceptor. So I'm trying to see how best can I assist you here with this one and show you how do we say this one is going now to produce a hydroxide ion. So when we talk of a base, I'm going to add it here. We usually say substance that dissociates. So what it basically says, when a substance dissociates, if it's a base, It basically means the substance is breaking now into two parts. So now consider us having a sodium hydroxide, of which is a normal base or a basic base that we know. So we say base now is going now to dissociate in order to form sodium plus now OH minus. So this basically now says to us, if it's a substance that is now producing hydroxide ions, and for this dissociation to happen, it must happen now in water. So it says, if this is the case, I have now produced my OH through the base that I know, which is the sodium hydroxide. So this now allows me to be in a position of explaining this particular situation. But when it comes now to Lowry-Bronsted says it must be a substance that is going to accept a proton. So if it's a substance that is going to accept a proton, let me take a base and an acid that we normally know. I'm going to take now HCl, react it now with a base which is NH3. So what is it that is going to happen? We know that an acid is a proton donor. So we are going now to have our NH4 plus now Cl minus. Can we now say this will be my acid and this will definitely be my base? Yes, we can. How can one be in a position of explaining this? Because this substance here accepted a proton from HCl. So now if a substance accepts a proton, it makes that substance now to become a base. So once we have in such a situation where an acid donated a proton and that proton has been now accepted by a substance, that substance that has accepted a proton, we call it now a base. So this is just an overview of understanding exactly what is it that Arrhenius theory emphasizes, as well as now Lowry Bronsted emphasizes. So it says to me, if I understand these basics, I can further move on and classify my acids in terms of a strong acid and a weak acid. So, but before I go into that, I want you to give me a confirmation by show of hands that you fully understand the two theories. You fully understand what is the difference between the two. They are only saying the same thing. Other one is focusing on the product being H3O plus in water. The other one is focusing now on the donation of a proton and the other substance now accepting. So I'm going now to allow you to show by hands that you fully understand everything. Thank you, thank you, thank you, thank you, thank you, thank you, thank you. Then it allows me now to move into the second part of this. Yes, you can ask that I'm listening. Who's talking? Okay, Jerry Mushala.
Base at the end of reactants ya sodium hydroxide OH.
Yes, sir. Because the rule the Arrhenius says is a substance that produces a hydroxide, and hydroxide ion is OH minus.
Highly acid subscript.
Highly an acid, it must be H3O plus. I don't want to say a subscript, but it must have H3O plus.
Okay, sir.
Thank you very much. I still see Musakwebu and Manuku Makama. Let me start with Musakwebu or Manuku, or you're just confirming that everything is fine. Manuku,
No, sir, I wanted to ask,
okay, you can ask me.
will it always be the case whereby the molecule that accepted enter
A proton.
the that accepted a proton will always be positively charged, and the one that lost a proton will always be negatively charged?
100%. Remember, what did we say? We said now, if you are losing electrons, you become more positive. But now this one is also gaining protons. So it basically says it's gaining a positive charge. So it will definitely become more positive.
Okay, sir, thank you.
Thank you very much. Now, with that being said, it says to me, I must also be in a position of classifying the relative strength of acids. What is relative strength of acids? We have acids that we classify as strong acids. We have acids that we classify now as weak acids. So as per definition, picture a question paper that says, define a strong acid or define a weak acid. So the key standard rule that we use, or the correct definition thereof, is this one that says a strong acid is a substance that ionizes completely in water to form high concentration of H3O plus ions. So for me to differentiate between an acid that is strong and acid that is weak, the only thing here is the amount of concentration of H3O formed, as well as is the substance now ionizing completely or incompletely. So if you check the statement here, let me get a highlighter. It says ionize completely in water. Ionize incompletely in water. So this is now the key difference in terms of why do we say the other one is a strong acid? Why do we say the other one is a weak acid? So it's a strong acid because now it's a substance that ionizes completely in water to form now what? High concentration. This is very key because it's an acid. It's also an acid. What must it do? It must produce H3 plus ions. So regardless whether it is weak, it is strong, the H3O plus ions must be produced, because if it doesn't produce now H3O plus ions, definitely it is not a base. How do we know that? We know that now from the two theories we have. So it is an acid because it produces H3O plus. That is the reason why. That is the key reason we need now to have the theories as a foundation of what we want to do. Fine. So the ATP, or the teaching guideline, says now we need now to be in a position of fully understanding or differentiating why an acid is considered to be strong and why another acid is considered to be a weak acid. So by nature, we have substances that we classify as strong acids. We have substances that we classify as weak acids. So I have given you a few that we normally use and work with. I've given you HNO3, H2SO4, HCl, and HBr. So all those, we classify them by, or we say they are strong acids. In an exam, you will be given substances of which you need now to classify whether they are strong acids or weak acids. If you see now you have H2SO4, you can classify H2SO4 as a strong acid. The reason why, the reason is it ionizes completely in water to form high concentration of H3O plus ions. If you see something like oxalic acid and ethanoic acid, we classify them now as weak acids. I will share the formulas later. Classify them as weak acids. The reason for that is they ionize incompletely. You'll find other sections or books will say they ionize partially to form low concentration of H3O plus. So the key idea here is to understand which ones are strong and which ones are now weak, and why do we classify them as weak. We will get to a point where each and every one of us must be in a position of classifying what is a base, what is an acid according to the two theories. At the same time, explaining now the relative strengths thereof. So there's a new pattern that is coming up of asking learners about the Ka value. So the Ka value is just a value that indicates how strong an acid is, or it's just a value that indicates the relative strength of an acid. So if my Ka is greater than 1, let's say something like 2 multiplied by 10 to power 5, it basically says this acid now must be a strong acid. If I am given 1 multiplied by 10 to negative 5, then automatically it says this value, it's less than 1. So if it's less than 1, I can be able to classify that acid as a weak acid. I'm going to put on my timer for 15 seconds for you to digest number 1 and number 2.
So,
Thank you. There's a question. There was a question. Okay, I don't see any hands, so it basically says we can proceed.
sir,
Yes,
Ka ke eng?
Jerry. Okay, I will repeat. Ka is just a value that indicates the relative strength of an acid. We call it an acid constant. We call it an acid constant. But you don't need to worry of how they came about this value. The only thing that you must just know is if the value of that Ka is greater than 1, it says now that acid, this acid here, must be a very strong acid. If that value you are giving, because they will give it to you, there will never be a point where the examiner asks you to now know what the Ka value or calculate the Ka value. The Ka value will be there. And the question will be, classify the following acid as weak or strong. Then you check if my Ka is greater than 1, then it basically says to me that should definitely be a strong acid. Siamo?
Yes, sir.
Yes, sir.
Yeah, I wanted to ask, when you are asked a question, will you be given the K value or only the chemical formula for the acid?
They can ask it in 2 ways. Ne? One is to give you a formula. Let's say they give you HNO3 and say, is HNO3 a strong or a weak acid? Is a strong acid, that you must know. And then the reason comes to say, explain your answer. Is a substance that ionizes completely in water to form now what? A high concentration of H3O plus. Now, you have a reaction, and this reaction, I'm going to write it down quickly, of the acid that we don't know. But they say HX plus H2O gives us now H3O plus now X minus. But the examiner further says for this reaction, the Ka is equals to 2 multiplied by 10 to power 10 for that matter. And the question is now, is this acid? Because we know it's an acid because it donated a proton. We know it's an acid because it produced the H3O plus. Now the question comes, is HX strong or weak acid? Explain your answer. Just because it produced H3O plus, it does not make it a strong acid, because we said also for a weak acid, it is a substance that ionizes completely in water to form low concentration of H3O plus. And we said strong acid ionize completely to form high concentration of H3O plus. So the fact that H3O plus is formed, the fact that H2O plus is formed, it tells us now we are working with H2O plus. It basically says we are working with an acid. But how can we tell now that HX is strong or weak? It becomes easy. We check now our Ka value. So if the Ka value is now greater than 1, then we agree that it must be a very strong acid. I hope that is clear.
Yes, it is clear.
Thank you very much. So I'm going to give you another 15 seconds for you to digest all this. Thank you very much. Then it means I can go to relative strength of bases. So remember, everything is based on the Arrhenius theory as well as the Lowry-Bronsted theory. So Arrhenius says a base is a substance that produces OH ions. At the very same time, Lowry-Bronsted says is a substance now that accepts a proton. So for this purpose, we are going to do the same thing also of explaining why others do we consider them as strong bases, why do we consider others as weak bases. So for us to do that, we say for one to qualify to be a strong base, it must dissociate completely in water to form high concentration of OH ions. So a definition basically of a strong base is what? Is a substance that dissociates completely in water to form high concentration of OH minus ions. When we look now at a base, which is a weak base, it dissociates incompletely in water to form low concentration of OH minus ions. So that is the first thing to look into. So even if the examiner tells me that substance A dissociates completely in water to form high concentration of OH minus, I will fully understand that the examiner is referring to a strong base. If the examiner says substance Y dissociates incompletely in water, automatically it should be an indication to me that I am now working with a weak base. But what if the examiner does not give me that particular statement? If the examiner doesn't give me that statement, it says to me, it's either they give me a substance that I can be able to classify. So I have few examples of which ones are strong and which ones are weak. So we say now sodium hydroxide, which is now sodium hydroxide is NaOH, is very strong. Potassium hydroxide is KOH, also very, very strong. So these are just few of the examples that I want us to note. And these are the ones that we commonly work with. But it's going to be advantageous and easy for us once we understand the basics of how can I classify one that is strong and how best can I classify the one that is weak. So ammonia, calcium carbonate, potassium carbonate, calcium carbonate, sodium hydrogen carbonate, they are all now what? Weak bases. Then also, like we did with the acid, we have the Kb value for this one. So the Kb value is basically a base constant. So the Kb value also indicates the relative strength of the base. So if the base or the Kb value is greater than 1, then it means that base, it is a strong base. If the Kb value is less than 1, it means that base I'm working with must be now what? A weak base. I will want to add another bullet here. I don't want to add it at this stage such that I don't give you a lot of information to process at once. Because we did say this topic also overlaps now to grade 12, where we talk of the pH value. So the pH value, I am not going to add at this specific juncture. I'm going to add it now later, once we are aware and fully understand the basic concepts hereof. So that's basically it about strong acid, weak acid. Strong base, weak base. We need to understand the difference between the two. But now the misconception comes. The misconception comes about concentrated acid or a base and dilute. People at most times think strong means concentrated. No. People at times think weak means dilute. No. We need to differentiate in such a way that we fully understand what is it that is changing. We can still have a strong acid, but that is dilute. We can still have a strong acid that is now concentrated. So the issue of strong and weak does not influence whether the substance is concentrated or dilute. That is the misconception that most people do. Previously, I did not have this slide, but when I went into the assessment guideline, I went into the mistakes that most of us are doing, is that we want now to classify concentrated with strong. We want to classify a weak with dilute. That is not how it is. A strong acid will remain a strong acid. A weak base will remain a weak base. A strong base will remain a strong base. The only thing that will change for the issue of one being concentrated and one being dilute is concentrated acid or base contains large amount of number of moles in proportion to the volume of water. So it basically says for one to have a concentrated acid, we need a high number of moles, a larger number of moles. So the larger number of moles, it basically says in proportion to water, less water, but now relatively, we need to compare the same amount of water for us to understand now the issue of concentrated and dilute. So the only thing that will influence that is now the number of moles. So if we have high number of moles of a substance, it informs us that now we are working with a concentrated acid or a base. If I look at a dilute substance, acid or a base, it contains small amounts or small number of moles in proportion to water. So if this is my 2 liters of water, and now this is my 2 liters of water, the water is the same throughout. But the only thing that is changing here should be now what? Large number of moles. Large number of moles. So with this, I can fully understand what is happening. Obviously here, it will be now what? Small amount of moles. Then I fully understand the difference between concentrated and dilute. It's not an issue of once you say it's concentrated, it means strong. No. Concentrated basically just means high number of moles in proportion with the volume of water. Dilute basically means small amount in terms of the number of moles in proportion to the volume of water. So I'm going to give you some time to process this after answering the question of Manu.
Sir,
Yes,
will we
Manu.
need to calculate the number of moles first, or are they always given?
Let's say, Manuku, because we are not at a section where we must calculate the number of moles. We are not expected to calculate yet because this is just a differentiation between the two. So when it comes a point of us calculating, we will be in a position of saying, if I add so much water, what will be the new concentration thereof? So those type of questions will come as an add-on as part of the complex stoichiometric calculations that we've been doing all along. So for now, let's just say it's just a matter of comparing and knowing when is it concentrated and when is it dilute. The issue of calculating will come as a base foundation of us knowing the calculations and the information we have.
Okay, sir.
Thank you. And now I see tab 8, the hand is up. Kindly start by introducing yourself so that we can know that who are we speaking to. Tab 8, your hand is up.
Dineo
Pomani. Next time you must just write your name, Dineo Pomani from Grassland. How can we help you, ma'am?
Ke ne ke botsa hore monana ho ha re identify hore na ntho concentrated le dilute ba tlo dila re fe setshwantsho jwalo ka re se fe mo or
I don't want to say they will give you a picture like I did for the purpose of explaining, but they can give you some hints in terms of the amount of water or the number of moles thereof. So the one with number of moles, but the water thereof must be the same. But the one with the smaller number of moles will be the one that is now dilute.
okay, sir.
Thank you very much, Dineo Pomani. So next time you may rename your tab to Dineo Pomani. Thank you very much. So I'm going to give you 15 seconds to digest this. Let me make it 20 so that we know now everybody is on par. Okay, now I see I have tab 8.1 and tab 8.2. Tab 8.2.
Good day, sir.
It's evening. Good evening. How are you? Kindly introduce yourself because we don't know who you are.
I am Khomele Mongkhwedi.
Khomole Mongkhwedi from Tsoseletso Secondary School.
Yes, sir.
Yes.
So I was asking, you know, if like you can only tell if it's concentrated or diluted if you have more of the, let's say, the base than there is of the water, or you have to compare the two solutions in order to tell the difference between the two.
You have to compare the two, but now it will be in terms of the number of moles. So if the one has larger number of moles for the same amount of water, it basically says that one must be concentrated. So when you compare the other one with the less number of moles, but for the same amount of water, it basically says that one must be dilute.
Okay, sir. Thank you.
Thank you very much. So I'm saying, let's not confuse ourselves with the picture. It will not come in a form of a picture, but there will be some information, some hint that is given to us in order for us to be able to classify which one is concentrated and which one now is dilute. Thank you very much. And Marshall Villagaz from into secondary.
Yes, good evening, sir.
Good evening, Marshall.
Sir, I was going to ask you about the concentrated acid or base. If we increase the quantity of water, would it still remain concentrated or would it be dilute since we'll be increasing the volume of water?
Definitely. Hence, they say here, concentrated acid or base contain large amount of water in proportion to the volume of water. So once you start now increasing the amount of water, it basically says the volume of water is increasing. So it will become now what? More water, less particles. So it becomes now dilute.
Understood, sir.
100%, Mr. Marshall Villagas.
Thank you.
So Khomolemo Nkhwedi, kindly take down your hand, and Pomani Dimpo, also take down your hand so that you can move on to the next session thereof. Thank you very much. Jerry?
Is large amount of number of moles make this concentration to be dim or
to be
Dim.
to
Yes,
be
dim in
not necessarily dim, it just makes it looks more richer than the other one. Think of your Oros in a 500 ml bottle and think of your Oros in a 1 liter bottle, but now you pour the same amount of Oros. So obviously the other one will look more stronger than the other one. So I don't want to say it makes it dimmer, but it gives it more body that is somehow very rich.
Oh, okay, sir.
Thank you very much. Khomole Mongkgwedi, your hand is still up. Do you still have something to say? Okay, Khomole Mongkgwedi, when you hear this message, kindly take down your hand so that you can move now to the other section.
Sir, I took down my hand. I don't know who's
Okay,
last.
so it's Dineo Pomane then. Thank you, Mr. Mongkgwedi.
Ah, say it is not me.
Then who is this tab 8? It's you. Thank you. Now let's move on. We started by saying we must have acid-base reactions. But now with acid-base reactions comes what we call conjugate acid-base pair. Conjugate acid-base pair. So this will take place when I have a reaction between an acid and a base. But how can one explain this fully and be in a position of saying exactly what is a base or a conjugate base and what is now a conjugate acid base pair? Let's start by saying we have two kinds. We have a conjugate base of an acid. So don't get lost. Let's understand this. It's a conjugate base of an acid. So I'm going to try and explain everything in terms of how can one fully explain the difference thereof. And how am I going to do this? Let me quickly get my pen. A conjugate base of an acid, we define it as an ion or a molecule. Ion or molecule that remains when an acid donated a proton. So an ion or a molecule that remains when an acid has donated a proton. And I must further add this information. If I have such a situation, it will be easy to see for me to identify which one is actually an acid. So I want to say a conjugate base will be one proton less. A conjugate base will be one proton less. So let's look into the reactions that I have. I have HCl plus H2O to produce H3O plus, and now gives me Cl minus. As per definition, it's an ion that remains when an acid has donated a proton. So that ion is this ion here. So basically the pair that I am looking for is the HCl together now with what? Together with HCl. Because if HCl donates a proton to H2O, it is producing H3O plus. Then immediately after producing H3O plus, it says here it's an ion or a molecule that remains when an acid has donated a proton. So if I donate a proton, I am left now with what? Cl minus. So that Cl minus here must be my conjugate base. So I will say now this is my acid 1, and now this is my base 1. And the information here also says a conjugate base will be one proton less. So if I check a B1, which is now Cl, it is short of now what? One proton, which is the H ion. So let me also now further add this other information at B. Let me change the color and use black. At B, let's say now conjugate acid of a base. Acid of a base. What must happen in this one? It must be now an ion or a molecule. Ion or molecule that remains when a base takes up a proton. But what does this say basically? It says if a base is going to take a proton, I am looking at the first reaction. I'm trying to reverse this reaction thereof. It says the fact that water accepted a proton, according to Lowry-Bronsted, it means now water must be my base number 2. Why do I know that? Because it did accept now what? A proton. So the fact that it accepted a proton, it makes it now to become a base. But looking into it further, it says now a conjugate acid of a base. I can say here now it should be a proton more, one proton more. And which one has now one proton more is definitely this one here must be now my acid number 2. So the 2, I can easily say these are my conjugate acid base pair. Now moving forward and looking into this, and checking exactly what happened, we can easily say, did water now on reaction number 2, did water donate or accept a proton? Very easy. Water donated a proton such that we move from NH3 to NH4 plus. So the fact that water donated a proton, it makes water now an acid. And we agreed that a conjugate base will be 1 proton less. So I am looking at a substance that is now what? 1 proton less compared to that one. So it must be this one that will be my base. So OH minus is a conjugate base of H2O. So these two, they go now hand in hand. NH3, is it a base or an acid? Clearly, it must be a base number 2. Why should it be a base? Because it accepted a proton from H2O. And we said now a conjugate acid base must be now what? 1 proton more. So it basically says I must have my acid now 2 being that one, and this will now become my acid base pair, conjugate acid base pair. I'm going to give you some time for you to digest this. I see 2 hands. Let me check who are those. Manuku.
Yes, sir.
Yes.
So, sir, actually, on the first reaction, H2O, they acted as a base, I guess. And on the second reaction, it acted as an acid. So, ribisa in highly jalo, it act as both an acid and a base.
We'll get to that. Thank you for your question. You are a step ahead a little bit. Let me take
Okay,
other
sir.
questions. Shabalala. Okay, it's okay. Tabisen Shabalala.
And I didn't know with ya manuku.
Oh, okay. So you are covered.
Yes, sir.
Okay, because I could not give a definition or what to say exactly about water before I could exactly show you why do we say at the first reaction it reacted as an acid, and on the second reaction it reacted as an acid. So for a substance like water, because it reacts at times as a base, it reacts at times as an acid, that substance, we call it an ampholyte. So what is an ampholyte? An ampholyte is, now it takes me now to my number 2 of what is an ampholyte. So ampholyte is a substance that can react as both acid and base. So an example thereof is H2O. But I want us to understand one thing. The fact that H2O is an ampholyte. It reacted as a base and as an acid. That does not quantify it all the times, because we have now substances like HSO4 minus. So the basic idea that I can give you is use now Lorry-Bronsted in order for you to understand that. In the first reaction, we see that H2O accepted a proton, so it must be a base. In the second reaction, we realize that what did it do? It now donated a proton. So that is the basic rule that all of us must use. So regardless of what type of a reaction you have, firstly look, did the substance now donate a proton? In the second reaction, did now the substance accept a proton? So if that is the case, is then that we can classify it as an ampholyte. So I don't want to say it will forever be water, it will forever be HSO4 minus. I don't want to say that. I want to say if you are given a reaction, kindly check, did it receive a proton or did it donate? But obviously you will need now to have what? Two reactions for you to compare. So if in the first reaction it donated and now accepted in the second reaction, definitely it now qualifies fully to be an ampholyte. So an ampholyte is a substance that can react as a base or an acid in a chemical reaction. If that is understood, then I'm going to give you another 30 seconds for you to digest all this information. Siamo?
Sir, I don't understand how to distinguish between the conjugate acid, the conjugate base of an acid and conjugate acid of
Acid
a
of a
base.
base. Okay, my brother.
Yeah, it's confusing.
Yeah, no, it is. Let's look into the first reaction, and we are going to try and explain the two. Now, the first reaction, you have
Yes.
HCl and H2O. And the definition of a conjugate base of an acid says it must be an ion or a molecule that remains. So what do we know? We know that an acid must donate a proton. So after donating a proton, what is it that will be left here? It will be Cl minus. So it basically says for a conjugate base, it is the remaining molecule or an ion of what? Of the acid after it has donated. So from the theories, we definitely know that HCl is going to donate because it's an acid. So what is left after donating? For instance, let's say I have my HCl here. So if it's going to lose that hydrogen, I am going to be left with Cl minus. So the Cl minus must be now my conjugate base of this particular acid. That is the first one. And I tried to make it simpler by saying a conjugate base will be 1 proton less. So if you have identified your acid, it becomes easy to look for a substance that is 1 proton less. So when I look at Cl minus, it has now what? 1 proton less. And then I further move on to say, let me see if I can be in a position of explaining what is a conjugate acid of a base. Ion or molecule that remains when a base takes up a proton. So that means it must be 1 proton more. Now, let's look at what happened in the first reaction. The first reaction, H2O accepted a proton, so it makes it a base. But now the second bullet here under conjugate acid says is a substance that is now what? 1 proton more. So if I look at H3O plus, it is 1 proton more than H2O. So that is how I can be able to identify a conjugate acid-base pair.
I still say it's still confusing.
Still confusing. Let's look at now reaction number 2. So with reaction number 2, we want to identify our acid first. Nesiamo. So for us to identify an acid, what do we use? We use Lori Bronsted to say is a substance that must donate a proton. Yes. So H2O here donated a proton. How can we tell? We are moving from NH3 to NH4. So it basically says NH3 accepted a proton. Ne?
Yes.
Fine. Now, we go to the definition. The definition says, whatever is left after the acid has donated, that must be a conjugate base. I repeat.
So, sir.
I repeat. Once we have our acid and it donates a proton, whatever that is left out of that acid, it becomes our conjugate base. Yes, yeah.
Yes, sir. I wanted to ask, with these reactions, you only follow them to the hydrogen protons? What? Yeah.
Hydrogen protons only, because the rules here that we are going to apply is that one of Lowry-Bronsted.
Yes.
Yes, sir. So once we have identified which one is an acid, it becomes easy because whatever is left of that acid after donating, it becomes your conjugate base. If you have identified now that this is a base, whatever that is formed, which is 1 proton more after gaining, must be a conjugate acid. So it basically says one will be proton less, and the one that is proton less, we call it now a conjugate base. One which is now 1 proton more, it must be a conjugate acid.
Okay, I see.
Thank you very much. Manuku.
Thank you, sir.
Sir, does this mean that anything that is conjugate is something that is in excess, like more than sufficient?
Nope, that is incorrect science. That is not the right way. The right way is to say for the two substances to be conjugate of each other, one should be 1 proton more, one should be one proton less, not in excess.
So does the word conjugate only appear in acids and bases, or does
Yes,
it appear anywhere else?
we'll only use it when we talk of acids and bases.
Okay, sir, thank you.
Thank you very much, Manu. Let me check who is saying something. Jerry?
So in other words, you're trying to say a conjugate acid of a base. It's a base that is formed when a reactant is a base accepts a proton.
100%. 100%.
Okay.
100%. Marshall Villagazi?
Yeah, so to make it really simple,
Thank you.
would it be fine if I say that the base takes up a proton and the acid donates a proton to just easily classify it?
That is basically Laurie-Bronsted theory, but we're not saying anything about the pair in terms of the other one being a conjugate base of the other one. So
I see.
yes, so don't give a definition of Laurie-Bronsted in terms of the acid. Basically just say after the acid has donated, whatever I am left with is going to be a base.
Huh.
Mm.
Understood, sir. Understood.
100%. Thank you very much, Mr. Marshall Villegas.
Yes, sir.
Siamo?
Sir, I
Yes,
think I found an easy way to identify it, sir. Ne?
help us then.
So I wanted to ask, ne, is it correct to say that a conjugate base of an acid is the product of an acid that is one proton less?
100% in that, because it's what the bullet number 2 is saying.
Okay, sir.
Thank you very much, Siamo. I am happy that now you fully understand. Manuku, is it a follow-up question or what is happening?
Yes, sir. Ke batla ho beha the way mina nka understandang ka teng ne.
Okay.
Akere naturally a base lose gain a proton,
Yes.
and then acid lose a proton. So
Yes.
in terms of conjugate, get the opposite, whereby a base gain a base lose a proton and an acid gain a proton.
Nope. That is not correct.
How so, sir?
And as remember the rules, the theories, we follow the theories at all times. So an acid will always be the one donating. A base will forever be the one accepting. We must just understand that for us to have a conjugate base, it basically says if I have an acid and that acid donates a proton, whatever I am left with must be a base, because it makes sense. We say we want to produce hydronium ions or H plus. So if I lose an H plus, let me write here H2O. If I am going to donate an H plus, what is it that I am left with here?
HO minus.
OH minus. So it basically says if I am donating the H plus, then I am going to remain with a base. Do you see that? Because I have
Yes, sir.
now already lost the H plus. So because the H plus is not there, I am left with the OH minus, and the OH minus is now what? A base. How do I know it's a base? It's a base because Lowry said it is a substance that produces hydronium hydroxide ions. So it basically says even if I have HCl and now Let me use this. Even if I have the HCl and the HCl donates this proton, what is it that I am left with?
Cl minus.
Cl minus. So the Cl minus becomes now what? A base. So this base, we call it a conjugate base of an acid.
Okay, so I understand.
Thank you very much. And I hope
Thank you.
everybody now is clear with that. Kindly open your mic and say, we are happy.
We are here.
Thank you
The
very
tag.
much. Thank you very much. And
We
if
are
you are,
here.
thank you.
Umoja.
No, if you are happy, I am also happy. So I'm going to clean this page for you. And then after cleaning this page, on my watch is exactly 2029. So it basically says this is enough for the day. Kindly go through the notes that I'm going to share immediately after this as a PDF document. Go through them and go through the books. You have a whole week for you to do that. And then next week we'll continue adding more other complex things. But I am happy that we spent more time on this, because this is the key foundation of how we do things. So we spend more time on the foundation, and then moving forward, everything becomes very, very clear. So the status quo still remains. Write your comments in the chat, and then such that I can be able to report. So I will forever keep on emphasizing the rules. Switch off your video, at the very same time mute your mic, and then we will be good to go. I understand we are doing this after a very hectic camp we had, but now let's not forget the basic rules thereof. So I'm going to take 2 hands just for the purpose of us closing this particular session. Manuku.
So going back to the ampholites,
Yes.
H2O and HSO4 minus, the only examples of ampholites.
No, they are not. There's a lot. But I didn't give you many because remember, we just want to comprehend the information. For one to clearly see or know if a substance is an ampholite, you need at least 2 reactions. Check, did it accept a proton? Did it donate a proton? If it did the 2, then it definitely means it must be an ampholite. So hence I said, these are not just the 2, it will depend on the structure of how we want to assess the question. But what you need to look for is for you to apply the basic principles, of which it must donate. On the second reaction, it must now accept, and then it qualifies to be an ampholite.
Does it include the brackets like the AQ, the liquids, and the gas? Had it affect the ions?
They don't, because it basically says you have a gas in a liquid, you have an aqueous solution also in a liquid. So it basically says you'll still have your ions in the solution.
Okay, sir, thank you.
Thank you very much. There's also another hand. Let me check who is that. It is Moho Matuku.
So I would like to ask, would I be wrong if I were to say a conjugate acid of a base would be an acid formed from a base?
100%. 100%.
Okay, thank you, sir.
Moho. Tiamo, are you closing the meeting for us?
Are you closing the meeting for us?
Sir.
Okay, then close your mic, sir. Thank you very much. So ladies and gentlemen, from me to you, thank you very much and all the best for the remainder of the week. And remember, we still have classes on Saturday through the University of Stellenbosch. We'll definitely meet on next week, Wednesday, but please be aware that we don't have much time, but there's quite a lot to do. So at some stage, we'll be required now to have sessions also on Fridays and Saturdays evening, such that we can fully prepare you for your final examination. As grade 11s for the Free State, I can put my head on the block and say you are going to write a common paper. So that common paper will be ready very soon. And yeah, it's going to be requiring you to give your all. Marshall Villagas, you are the last one so that I can close this session.
Sorry, sir. I was going to ask you, will we be having a lesson this Friday, like an online lesson?
Like for me?
Yes.
No, that day, Villagas. We will wait for next week because we'll still have to communicate it with other tutors, especially for mathematics. So have your sessions of maths tomorrow. And we wanted to start this one now so that the new people, Bohomolemo and Anati class, and they can now be in a position of knowing how we operate. Then we will expand more and introduce more slots and time sessions as we move forward.
Okay, understood.
Thank you very much, Marshall Villagas. Ladies and gentlemen, good night.